Okay, substituting, we will have, instead of AL substitute this, instead of BL substitute this expression, you will have this solution. So this minus and minus will become plus, so it's written as plus, R tends to 0. Now very important thing is, for physically acceptable wave function, if R tends to 0, the wave function should exist. If R tends to infinity, the wave function should disappear. We learnt in the interpretation of wave function in quantum mechanics 1. Okay, for any wave function, when R tends to 0, it should exist. When R tends to infinity, it should disappear, it should vanish. We know already. So substitute R equal to 0 here in this expression. When R equal to 0, the cosine term will go off. It will be 0. It will become 0. So this is your complete radial function. I repeat, when R tends to 0, the wave function should exist. For example, sin R by R. When R tends to 0, the answer is 1. When R tends to infinity, the answer is 0, sin R by R. So which is not acceptable wave function. For any acceptable wave function, the wave function should exist when R tends to 0, when R equals to 0. So similarly, you substitute R equal to 0 here, this term will go off, cosine term will go off, only there exists only this term alone, sin R by R, sin KR by KR. So according to this, we can write the complete solution as this. Okay, so we are going to use only this radial part, this equation alone. So if del L equal to 0, your RL radial part is finite at R equal to 0 because it reduces to Bessel function. So del L is a real angle, phase factor, which vanishes for all values of L in the absence of scattering potential, which is nothing but V equal to 0. So del L is nothing but your phase shift. Okay, phase shift from the incident plane wave, and this wave is called a distorted wave with a L. Now we will explain what is phase shift. Okay, now, so before that, you just look at this equation. Look at this equation. This can be combined with like this: sin A plus B. Sin A plus B equal to this factor. Then another term will become 0. Okay. So this can be combined with KR minus L pi by 2 plus del L by KR. So we have written together, we have written as this. So this will be a complete radial part solution. Now what is a phase factor del L? So I will have small figure to explain this one. Suppose if there is no potential, you consider this, there is no potential. The wave function is your sine wave function. Okay, the peak is exactly denoted as a red line. So this is your peak for a free particle. Free particle means, of course, there will be no potential. Okay, the wave function goes like this, and we have drawn the graph between your interaction potential U of R with K of R. Okay, we have drawn the graph. Now the peak is denoted as this line. Okay, this line, and it ends with 0 in this part. Okay, in this point, the first point. Now, for example, you consider the potential is attractive. Here there is no potential. Here there exists a potential which is nothing but an attractive potential. Attractive potential is minus V naught. Repulsive potential is plus V naught. So now we are going to compare these two with the free potential. So suppose if you are going to have the attractive potential minus V naught, then the peak shifts towards this side, towards left. See, the peak is here, but peak is here is lagging. It shifts towards the left side. What of the 0 point? That also it goes, see, little bit lagging. See, 0 is somewhere here. Whereas for this wave, 0 is shifted towards the left side. This is known as phase shift. That is a positive phase shift. Okay. Similarly, when you are going to take the potential, that is positive potential, then look at the peak. Peak shifts towards the right side. And also the point where it meets 0, that also shifted towards the right hand side, and this shift is nothing but your negative. So phase shift is negative. Here phase shift is positive. So this is the way that we can learn the phase shift. Okay, the phase shift is very important because we are going to collect all the waves, interfere, and we will get the scattered wave. So L equal to 0, 1, 2, 3, so on. So what we call this is a distorted wave function. So distorted wave function, which is nothing but 6.96 when the inclusion of phase shift is given by exactly like this. So we have a radial part, we have a angular part, okay, spherical harmonics, and of course AL equal to CL divided by root 2 pi. So we know already. So this is your complete wave function. Okay, now expand, as usual we have expanded this one. So expand in terms of exponential. So expand sign in terms of exponential. So you have e power minus L pi by 2 can be written as minus I to the power L. So e power IKR, e power I del L. So first part is over. Minus this will become plus. So e power I L pi by 2 can be written as I to the power L. This can be written as e power minus IKR. This can be written as e power minus I del L divided by 2i. Okay. So this is replaced with this expression. So this equation can be written as exactly like this. Equation 6.121. Any doubt? So you have AL, PL cos theta. This is replaced with this expression. So you have this expression. Any doubt? Equation 6.121. Now, so again as usual, we can write this as one part. We can write this as another part. As usual, earlier we have written the same thing. So we have this part and another part. So I have replaced this part here and second part to first part and first part to second part. The reason is we have already seen this equation earlier with a minus sign front. So that's the reason that I have shifted. So I repeat. So we have written this part as first part and this part as second part. And in the next one I have written as second part as first part and first part as second part. Okay, now we are going to compare this equation with this equation. Our ultimate aim is to find out f of theta using wave function, using solution of the wave function. So this is what we did in Born approximation too. The same thing we are going to apply. Okay, now you just compare this equation with this equation. You compare this. When you are going to compare this equation, we can get the value of or expression of AL. We can get the value of AL. You compare the first term with the first term, second term with the second term. Come on, first term you just compare. So this is your AL I to the power L, AL I to the power L, e power minus I del L. Remaining term will be same thing. So you have a PL cos theta will be the same thing. E power minus IKR divided by 2IKR is the same thing. 2IKR will be the same thing. The remaining term, right, this side you will have I to the power 2L, 2L plus 1. See? Okay. So I can bring this I to the power L that side. So that will give us I to the power minus I. So I to the power 2L minus L, that will give us I to the power L. E power minus I del L becomes e power plus I del L. So AL, we will have the expression of AL is exactly like this. So we have found out the expression for AL. We can substitute. So we can substitute in equation 6.123, and we will have, instead of AL, we are going to substitute I to the power L, 2L plus 1, e to the power I del L plus the remaining term. Is it okay? So you have exactly, I have written the same thing. 1 minute. So e power IL, that can be written as e power I2L. E power I del L, e power minus I del L will give us 1. So that can be written as like this. Second term, for the second term again simplify as e power IL multiplied by minus I to the power L becomes 1. And this one can be written as e power 2I del L. So 2I del L. Is it okay? So the equation is here. Okay. 2I del L. Anything, any doubt? Now you are going to compare this equation with this equation. We know already this equation earlier. You compare these two equations and we can get the expression for your f of theta. Come on. Compare this equation. First term is equivalent to first term of this equation. So this is equation 6.127. This is equation 6.109, which you already learned earlier. You compare these two equations. First term is equal to first term. See here, left hand side is equal to left hand side. So second term must be equal to second term. So you can write second term as f of theta plus 1 divided by 2ik sigma 2l plus 1 pl cos theta, which is equal to this term. So 1 by 2ik, e power ik r by r is common. So 1 divided by 2ik sigma over 2l plus l e power 2i del l pl cos theta. Is it okay? Bringing the second term of left hand side, this term to that side. So we can get the value for f of theta. So our aim is to find out f of theta. Just bring this term to that side. So f of theta is given by this. Taking the common term out, the remaining term will be e power 2i del l minus 1. See, just take the common term out. So e power 2i del l minus 1. Okay. Now, so I am going to take 2y inside. See here, 2y inside. E power 2y del l minus 1 divided by 2y. I am going to simplify this part alone. 2y e power 2y del l minus 1 divided by 2y, which is equal to, I am going to simplify this term. Listen to me, I am going to simplify. See, 1 is replaced with e power I del l multiplied by e power minus I del l. And here we have e power 2i del l. Okay, I am going to take 1 e power I del l out from both expressions. So we have expressions for 1, I can write this. For e power 2i del l, I can take 1 e power I del l out. So this equation can be written as e power I del l multiplied by e power I del l minus e power minus I del l divided by 2i. So this is termed as sin del l. So e power I del l sin del. So this term is replaced with e power I del l sin del l. So f of theta becomes 1 by k sigma over l equal to 0 to infinity 2l plus 1 e power I del l sin del l and your pl cos theta. Okay, pl cos theta, which we are going to term as f suffix l, fl of theta, because it depends on l. Summation over l equal to 0, it means to infinity. So it means l equal to 0, 1, 2, 3 goes on. That's why written as f suffix l of theta. So this is termed as partial wave amplitude. Is it okay? So almost we have come to the end. Okay, f of theta. So it is a basic result of partial analysis which gives us scattering amplitude as a sum of contributions from all partial waves. So squaring of scattering amplitude will give us differential cross section. Okay, differential cross section. So now squaring is very important. Just look at the expression. We are going to square this term. When you are going to square the term, 2l plus 1 becomes 2l dash plus 1. When you are going to square this one, it becomes e power I del l multiplied by e power minus I del l. So don't forget. So this squaring of this term will be del l. So del l dash, sin del l means sin del l dash. PL cos theta, when you are going to square, that will become PL dash cos theta. You will have to write corresponding its complex conjugate when you are going to square it. So we have written exactly like this. So this is the term 1 by k multiplied by 1 by k. So that becomes 1 by k square. 2l plus 1, 2l dash plus 1. E power I del l becomes e power minus I del l. Sin del l becomes sin del l dash. PL cos theta, PL dash cos theta. Is it okay? Now we are going to have the total differential cross section, which is given as this expression. Okay, we know already. We are going to integrate, that will give you total cross section. We know already. We are going to use spherical polar coordinates. When you are going to use spherical polar coordinates, that will give us, this is for theta 0 to pi, this is for phi, that is 0 to 2 pi. And of course, that will give us answer as immediately as 2 pi. So 2 pi f of theta whole square sin theta d theta, we are going to substitute to get the total cross section, the expression for total cross section. So which is given as like this. So this is for one part, this is for squaring. So we'll have to square the term. So 2l plus 1 multiplied by 2l dash plus 1. E power I del l multiplied by e power minus I del l will give us this. Sin del l dash. PL cos theta, PL dash cos theta, sin theta d theta. Okay. Is it okay? And of course this 2 pi comes because of 0 to 2 pi d phi. Integration of 0 to 2 pi d phi. Is it okay? So we are going to use orthogonal property of Legendre polynomial, which is given as which is given as 2 divided by 2L plus 1 del L L dash, which you have already learnt in mathematical physics. So orthogonal property. So substitute orthogonal property here. So 2 divided by 2L plus 1. Okay, here just multiply when L equals L dash. This will become 2L plus 1 whole square. Correct? When L equals L prime, L dash, we have 2L plus 1 whole square. This 2 divided by 2L plus 1, we are going to replace this one. So 1 2L plus 1, in the numerator 1 2L plus 1 will get cancelled. So we have only 2 multiplied by 2 pi will give you 4 pi, this k square, 2L plus 1, the remaining term. When this is equal to answer will be 1. So your sine square del L. I repeat, this becomes L equal to L dash, this becomes sine square del L. Okay, that part is over. This part will be 1. And for this part, you multiply these two, 2L plus 1 whole square, that will be cancelled with 1 2L plus 1. So we have only 2L plus 1. These 2 multiplied with 2 pi will give you 4 pi. So this is your total expression for your total cross section. Sigma t, which is equal to 4 pi by k square, summation over L equal to 0 to infinity 2L plus 1 sine square del L, where del L dash are the partial cross section which correspond to the scattering of particles in various angular momentum states. The differential cross section, this one, consists of superposition of, that's why summation, superposition of terms with a different angular momentum state, L equal to 0, L equal to 1, so different angular momentum states. So exactly as given, it gives rise to the interference pattern. So this is what right from the beginning I have been discussing, interference pattern between different partial waves corresponding to different values of L. Okay, any doubt? So this is the last final expression which is very important. Now, what are the ideas? When V equal to 0, all the phase shifts del L will vanish. Hence the partial and total cross section will be 0. So for there is no potential, the phase factor will disappear, and ultimately the partial and the total cross section will become 0. And for del L equal to 0 or pi, you substitute del L equal to 0, sine 0 0. So sigma t will become 0. So there will be no total cross section. When del L equal to pi by 2, sine 90, sine 270, answer will be 1. So that will have maximum value. The phase shift is a function of k. Okay, wave vector. Each term in the sum is a contribution of L to partial. Okay. Now another very important idea, we are going to have only S wave alone for the simplicity, for low scattering when L equal to 0. Suppose if L equal to 0, your P0 cos theta, P0 cos theta becomes 1, which we already legendary polynomial, P0 cos 0 equal to 1. So that expression becomes 1 by k e power I del 0 sin del 0. That term is termed as 1. Okay. Squaring this term will give you differential cross section. Squaring this term. So when you are going to square, this will become a complex conjugate. So both will cancel. You have only 1 by k squared sin squared del naught. So your total cross section becomes 4 pi. You have to multiply with 2 pi. Correct? Another one too. So we have 4 pi divided by k squared sin squared del naught for S wave. So this is the answer for the total cross section for the S wave. Okay. When theta equal to 0, the total cross section is related to the forward scattering. So we learnt already e power I kr k dot r e power I kr cos theta. When theta equal to 0, it means that this is undeflected one. It goes forward. So in that case, you just expand this one. E power I del L can be expanded, cos del L plus I sin. This screen is very important. This question may appear in section A, small question. Okay, what is optical theorem? Okay, optical theorem is very important one. I repeat, e power I del L can be expanded when theta equal to 0, very small. This can be expanded like cos del L plus I sin del L. You multiply these two. Multiply 2L plus 1 with this factor and multiply 2L plus 1, that factor will give you real part plus imaginary part. So I have separated now. I have separated real part as and imaginary part. I am going to take only imaginary part alone. So what is imaginary part here? Which is nothing but 1 by k. These are all common. 1 by k, 2l plus 1. The imaginary part will be sine squared ll. Okay, sine squared ll. And we know already sigma t is expressed as exactly like this. Now, just take 4 by divided by k. And you have 2l plus 1 divided by k. This k square I have separated to k and k. 4 pi divided by k, 2l plus 1 divided by k sine squared ll, which is nothing but your imaginary of f of 0. Theta equal to 0. So f of 0. So your total cross section becomes 4 pi by k. The remaining one will be this one. Imaginary part of f of 0. I repeat, your sigma t is given as this expression. Instead of k squared, you can write k into k. So 1k I have kept it here, another k I have kept it here. 2l plus 1 divided by k sine squared ll will give us imaginary part of f of 0. So your sigma t becomes 4 pi by k imaginary part of this function, imaginary part of f of 0. This equation is known as optical theorem, because we are going to concentrate only on imaginary part. Optical theorem, which we learnt already in optics, especially in changes of refractive index, we have already learnt. So this refers only absorption coefficient. For any absorption coefficient, we will be giving much more concentration only on imaginary part. So that's why this is termed as optical theorem. So the optical theorem relates the scattering amplitude in the forward direction to the scattering cross section. Okay. So when theta equal to 0, which is the incident wave direction, and sigma t becomes, the total cross section becomes exactly like this. So f of 0 is the forward scattering amplitude. The total cross section is given by 4 pi by k times the imaginary part of forward scattering amplitude. This is forward scattering amplitude. The imaginary part multiplied by this factor will give you total cross section for this case, theta equal to 0. So optical theorem is a reminiscent of similar theorem in optics, just now I said, which deals with the scattering of light. The physical origin of this theorem is conservation of probability. So it refers only conservation of probability. So number of particles which are incident should be equal to number of particles which are scattered plus unscattered. So this is called conserve. For example, just take incident particle, number of particles in the particle is 1000. Just consider. So if 900 particles are scattered, the remaining 100 particles will be unscattered. So you add these two will give you 1000. Okay. So this is called conservation of particles. Of course, total cross section or differential cross section will give us number of scattered particles in the cross section. Okay, in the solid only. The beam emerging after scattering along the incident direction theta equal to 0 contains less particle than the incident beam, since the number of particles have scattered in various directions. So this is what I said. 900 plus 100 will give you 1000. 1000 equals 100 plus 900. 1000 particles are there. If there are 900 particles are scattered, the remaining particle will be unscattered, undeflected. So the last slide, this decrease in the number of particles is measured by the total cross section sigma. That is nothing but number of particles removed from the incident beam along the incident direction is proportional to sigma or equivalent to the imaginary part. Okay, imaginary part of your scattering amplitude. So optical theorem, as I said earlier, is analog with the relation in optics between the absorption coefficient, which is always related with the imaginary part, and the imaginary part of the complex changes of refractive index. So which is nothing but index of refraction. So that is the end of this lecture. This lecture is very, very important one, and this is about a partial analysis, okay, which is different from Born approximation. In Born approximation, we dealt only with the weak potential. Here we are not going to consider any weak potential. This will work out for all the potential. So that's the main idea, and we have obtained the scattering amplitude and also total scattering amplitude, and thereby differential cross section. Okay, so thank you students. We will see in the next class.